Hello everyone. So today in this video we are going to look into the stereochemistry of compounds with two chiral centers. So far we have been discussing only about one chiral center. So in this video we will look into the two molecules with the two chiral center. To start with, we take the example of the 2,3-dibromobutane. So when we write the condensed formula, we quickly understand that there are two stereocenters present at position 2 and position 3. Okay. So once we understand there are two stereocenters present in this molecule, we can calculate easily how many stereoisomers we can write for this particular molecule. So if we look here, the formula that we use to calculate the number of stereoisomers is nothing but 2 to the power of n. So n is the number of stereocenters present in the molecule. So in 2,3-dibromobutane, the number of stereocenters present is 2. So therefore, the number of possible stereoisomers that we can draw for 2,3-dibromobutane is nothing but equals to 4. So after knowing the number of stereoisomers that we can write for 2,3-dibromobutane, now the next job is to represent and draw these stereocenters. So how we draw them? We know there are two basic formulas that we use for drawing a three-dimensional molecule on a two-dimensional plane, either a perspective formula or another would be a Fisher projection formula. So when we consider these two formulas, let us see which is more convenient for writing molecules with more than one chiral center. So let us first start with the perspective formula. So for your convenience, let me write the numbers of carbon atoms. So it is 1, 2, 3, and 4. Okay, so it is 2,3-dibromobutane. Now, whenever you draw a perspective formula with a long carbon chain, we prefer to write the carbon chain on the line bonds of a perspective formula. So that is what I have done here. So I have tried to write the structure in such a manner that the carbon chain is falling on the line bonds in a perspective formula. So since there are two chiral centers present, that is position number 2 and position number 3, therefore I have drawn the corresponding perspective formulas at the two stereo centers. Now, after placing my carbon chain on the line bond, the next thing that I have to do is arrange the substituents. So when I come to the second carbon, which is your stereo center, that is the first stereo center, it is attached to two substituents. One is your hydrogen and another is your bromine. So initially, to start drawing it, let me put H here and Br here. Okay, once I write like this, the next point, that is the next stereo center, is carbon number 3, and this is again attached to H and Br. So this time what I'll do is instead of placing H on the dash bond, I'll place it on the solid bond and write the other bond with the Br. Okay, once I draw this perspective formula, next job is to draw the mirror image. So mirror image should, a perspective formula should look something like this. Once I draw this, then since H is on the wedge, in the mirror also it would be on the wedge. Br is on the solid wedge, so in the mirror also it would be on the solid wedge. Coming to the second stereo center, that is the third carbon. Here again, Br is on the dash wedge, so here in the mirror image also it will be on the dash wedge. However, the hydrogen is on the solid wedge, therefore here again it would be on the solid wedge. So now these things are pretty uh, simple to understand and write the mirror image, and you are also now pretty acquainted with how to write the mirror image of any possible stereoisomer. So, okay. So thus we have, there are how many stereoisomers possible? There are 4 stereoisomers possible, and we have already drawn the 2. One is this molecule and second one is its mirror image. Okay. Now we will do the alternate arrangement. So I keep the configuration at the first stereocenter same. So I draw something like HBr. Okay. Now here what I did was H I placed on the solid wedge. Here I again change a little bit. Otherwise it would be the same as the first one. So H on this dash wedge and Br on the dash wedge. So this would be my second second variant of the stereoisomer. And if I draw the corresponding mirror image, so again hydrogen is on the dash wedge. So here also it would be on the dash wedge. Here again it would be on the solid wedge. Here solid wedge and hydrogen on the dash wedge. Okay, so I have drawn 4 possible stereoisomers for 2,3-dibromobutane. Perfectly fine. So this much is perfectly clear to us, and we have drawn the 4 possible stereoisomers for this molecule. Then the next job to identify is whether these molecules are chiral. So far we have only dealt with molecules with only one stereocenter. So whenever the molecule is having only one stereocenter, then the molecule is always chiral. The molecule is always chiral. But when it comes to molecules with more than one stereocenter, then we need to look it through a different perspective. For example, so how we can decide whether these molecules are optically active or inactive, or in other words, whether these molecules that we have drawn just now, these 4 stereoisomers, are chiral or not chiral. So that would be decided on the basis of certain rules. Okay, so here I have written down certain rules, conditions which can decide whether a molecule is optically active or not. One of the condition is if the molecule has only one asymmetric center, then that molecule is definitely chiral and therefore optically active. So that is what we have been seeing so far, that whenever we talked about the presence of a chiral center, we automatically said that the molecule is chiral. Okay. Now, the second criteria which can decide whether a molecule is optically active or not is that molecule and its mirror image are non-superimposable. This we started understanding in the first part of our understanding of stereochemistry, where I told you that optically active or chiral molecules are always optically active. So what are chiral molecules? Those molecules whose mirror image is non-superimposable. So that is the second criteria by which we can decide whether the molecule is optically active or not. The third criteria by which we can decide whether the molecule is chiral or, in other words, optically active is whether these molecules contain the symmetry elements like plane of symmetry or center of symmetry, which is represented by letter I, or alternative axis of symmetry like Sn. So if these symmetry elements are present in the molecule, then definitely that molecule is not chiral, or they would be optically inactive. Okay, so here what we see is that our 2,3-dibromobutane has asymmetric center present in them. Now, I'm not going to call them as chiral center because I'm going to just now show you that these 2 molecules, that is 1 and 2, they are optically inactive. Okay, so how that is so, I'll show you in a short while. So with that concept, with that fact in mind, now I cannot call these as chiral center. Now it is better always, that's why, to call the centers, carbon centers, which is attached to four different groupings as asymmetric center, or more general term would be a stereo center, rather than calling them as chiral center. Chiral center was a terminology that was used in the older times. But since we started understanding the stereochemistry more better and better, so we need not want any kind of confusion in the terminology. So that's why for you guys, it is always safe to use terms like stereocenter or terms like asymmetric center. But more better term, more general term would be stereocenter, because asymmetric centers sometimes get confused with the asymmetric molecule, which I'll be talking later on, trying to discuss with you what is the difference in terminology like dissymmetry or asymmetry. Okay, which I'll talk in the another video. Since it's just a general understanding, we no more use those terms. We are sticking ourselves with stereo centers these time. So in modern textbooks, you'll find the use of terms like stereo center more than the use of chiral center or asymmetric center, which are used very less in the modern textbooks that you will find connected with the organic um, organic chemistry. And often Indian author books still uses these older terminologies, which are not prevalently used nowadays in the use of stereochemistry. So continuing further, so we understood like what are all the factors which decide whether a molecule is optically active or not. So let us try to use this second condition, that is molecule and its mirror image should be non-superimposable. So let us check whether 1 and 2 are non-superimposable or not. So if you want to understand, it's not so simple to understand this particular figure because it's drawn in a perspective formula, but I'll tell you now how to understand that. If you consider an imaginary axis on this particular writing plane, passing through the midpoint of C2, C3 bond, okay, C2, C3 bond, consider an axis that is passing through the midpoint. Okay, and if you rotate along this axis by a axis of by a clockwise direction by an angle of 180 degree, okay, what you will see is that the configuration that you get would be same as this particular molecule. Okay, so that is why I am saying that these two are superimposable on each other. Now, this particular thing that I just now said to you, I would like you to try, okay, and find out for yourself whether you are getting this or not, okay, or any other way in which you can rotate and show that this particular stereo isomer, that is 2, is superimposable on 1. Okay, so that is what I would leave to you to exercise yourself. Okay, and let us look at this particular molecule. When we look at this particular molecule and we do similar kind of operation here and try to bring this molecule closer to this, then we find that these two are non-superimposable. So these two figures that you see here are actually non-superimposable. Non-superimposable. Okay. However, these two structures, these are basically superimposable. So if these two structures are superimposable, then that means these are optically inactive. These are optically inactive. Sorry, because of the slowness of the net sometime there is a lag in the writing. So optically inactive. However, this is non-superimposable. Therefore, this two stereoisomers that we have drawn, that is stereoisomer 3 and stereoisomer 4, these are chiral molecules, or we can say they are optically active molecules. Okay, now this is the prospective formula we just now discussed, and we find that the visualization of these molecules and understand how to understand whether these images are superimposable or non-superimposable, it's very difficult to understand when it comes to a, a kind of perspective formula. So it is more better whenever we have more than one chiral center present or more than one stereo center present in the molecule, then it is always advisable to use Fisher projection formula instead of the perspective formula. Now you will understand why I am saying so. So let me draw the corresponding Fisher projection formula for each of the perspective formula that is drawn above. Okay, so if we look here, we find that I am keeping my line bonds, that is on the vertical bond of the Fisher projection formula. That means the carbon chain is on the vertical bond. So let me number it exactly in the way it is numbered in the perspective formula, and that is 1, 2, 3, and we have the 4. Okay. Now, the next thing is to understand how it is attached, the substituent, how it is attached. So the way we did in all the conversion, that is the same thing we are going to do. So initially, in order to understand, we will consider each of the stereocenters separately and draw the corresponding Fisher projection formula. So let's consider first the stereocenter, which is located on carbon number 2. Okay, so when we look here, how we did do that, we will consider axis which is passing through carbon number 1 and 2, and we rotate this anti-clockwise. We rotate this anti-clockwise. Let me draw that again. We rotate this anti-clockwise. So when I rotate it anti-clockwise, what I see is BR is coming on the right side. So BR is coming on the right side, and obviously the H would be coming on the other side. Okay, that is on the left side. Okay, now let's consider the second stereo center, and which is carbon number 3. We will consider an axis that is passing through carbon number 4 and carbon number 3, and we rotate again by anti-clockwise direction. When we rotate by anti-clockwise direction, this H will be coming on the left side. So H would be coming on the left side, and therefore the BR would be definitely on the right side. Okay, so I can directly convert my perspective formula into a Fisher projection formula. Only thing is, it is done in the same way as you did for the one asymmetric center. Only thing is, when you consider to draw the Fisher projection or the substituent at one stereo center, you consider only that particular stereo center in the perspective formula and try to rotate it and see how the substituents are moving. Once you understand that, and accordingly, you will put the substituent on the stereo center. Similarly, let us look here. Let me do that again for you. So 1, we have 2, then we have 3, and then we have the 4. So again, if I consider this particular axis and try to rotate in clockwise direction, the BR would be coming on the left side. Obviously, the other substituent is my hydrogen would be coming on the right side. Similarly, for drawing the second stereo center, again, I'll go using the clockwise direction. My H will be coming on the right side, and Br would be on the left side of the molecule. Okay, now see here you can visualize also the mirror image perfectly. Okay, so perfectly you can see that structure number one, the structure number one and structure number two both are mirror images of each other. We can perfectly understand it by seeing the uh, Fisher projection formula. So that is why this Fisher projection is very much easier and simpler to use when it comes to multiple stereo centers. Now, let me also finalize 3 and 4 structures. So let me do it quickly. So Br would be here and H would be here. Second structure, Br would be here. Now, I would like you to do yourself how it is done so that in the examination when it comes, you are perfectly clear about how to do it. So I'm directly writing it, but in examination when it comes, you're required to give me how you are arriving at a particular Fisher projection formula, not just simply write the Fisher projection formula. You should show me how you are coming to that Fisher projection formula. So here you see, I have drawn the Fisher projection formula of all the 4 stereoisomers. So just now I told that these two are the same molecule. How can I understand easily from a Fisher projection formula? So in a Fisher projection formula, as previously I mentioned a certain important criteria that if you rotate a Fisher projection formula by 180 degree in the plane, okay, by 180 degree in the plane or in the writing plane, if you rotate the molecule, then you do not change the configuration of the molecule. Or another thing is at a stereo center, if you do even number of interchanges, then you do not change the stereochemistry or you do not change the configuration of the molecule. So that is what I'm trying to do here. So if I rotate this particular second stereoisomer by 180 degree in the writing plane, which is an allowed operation, then I do not actually change the configuration of this molecule. And therefore, whatever structure I'm going to get would be same as the second structure. Okay. So when I do the 180 degree rotation, what I find is that since both are CH3, when I do 180 degrees rotation, it would be CH3 only. To distinguish and to make it more clear, let me put a cross here and let me put on the third side a box here. So when I do the 180 degree rotation, my box will be coming up and my cross would be coming down. Okay. So when I do this 180 degree rotation, my H would be coming on this side and Br would be going on the other side. So I get my H here and I get my Br on the other side. Okay, so what do you see in this structure? That the stereoisomer 2 is exactly the same as stereoisomer 1. So that means these two structures are actually same molecule. It's only we have written it in a different fashion, that's all. But these two molecules are superimposable on each other, which we can easily understand from the Fisher projection that these 1 and the 2 are superimposable on each other. 1 and 2 are superimposable because when we do the allowed operation of 180 degree in the plane, it is not changing the configuration of the molecule. So if we see this particular Fisher projection formula is superimposable on the stereoisomer 1. Therefore, these two structures, that is 1 and 2, are actually same molecule. Okay, so therefore we have one of the stereoisomers, the number of stereoisomer is reduced by 1 because 2 of the stereoisomers are same. Okay, so we can I'm going to write just one structure here, that is HBr and again H and Br. Now remember that the I can write Br, this structure also here, Br and HH, same thing only because both represent same molecule. There is no change in the configuration. Therefore, instead of 4, it is reduced by 1 here because of the presence of this kind of optically inactive molecule. Now let us look at this particular structure, that is 3 and 4. If we look at these molecules, we find that when we do a similar kind of operation on stereoisomer 4, we find that it is not superimposable on the third stereoisomer. So that means these two are different. These two are different. So I'm going to write exactly my stereoisomers like that. So I'll write HBr. Okay, here again I'll write Br and then H and H and Br. So initially when we started drawing the stereoisomers for 2,3-dibromobutane, we found that there are 4 possible ways to write it. Okay, but after looking at the structure in detail, we found that the 2 of the structures are the same configuration. Therefore, now if you are asked how many stereoisomers you can draw for 2,3-butane, you will say only 3 possible structures are possible. Okay, so how many stereoisomers are possible for 2,3-dibromobutane? Only 3. Though there, when you write about the stereoisomers, you will start by using 2 to the power of n formula. You will come and write the 4 structures. But finally, in the final answer, you should write that only 3 are the stereoisomers possible in the case of 2,3-dibromobutane. So let us try to understand the third. So this is on the basis of the non-superimposability of the mirror image. Let's look at this particular fact, that is the symmetry elements like uh, symmetry plane. Okay, symmetry plane you might have seen. So if you look at this particular stereoisomers, you can find that if you draw, if you place a mirror at the center of this carbon chain, you find that the top one would be exact mirror image of the bottom side of the molecule. So even this one you can see this kind of symmetry plane. So this kind of plane, if it exists in a molecule which is able to mirror image both ends of the molecule, then we say that this molecule, this particular stereoisomer contain a sigma plane. Therefore, this is optically active. So whenever you have a symmetry elements like plane of symmetry present in the molecule, then these are optically inactive. So here, since we have a plane of symmetry where the top part is exact mirror image of the bottom part of the molecule, therefore this is optically inactive. So due to the presence of a sigma, this is inactive. So you might have studied that sigma is equivalent to an alternating axis like S1. Okay, so S1, so again, if alternating axis is present or a mirror plane is present or a center of symmetry is present, whenever these symmetry elements are present, we will say that these molecules are optically active. But if you look here, in these two stereoisomers, that is 2 and 3, you will find that they do not have any symmetry elements present in it, no plane of symmetry. You try and see for yourself whether you can come across any symmetry elements. If you can, please let me know in the live session. And from my understanding, these molecules do not have a symmetry element, okay? Like sigma I or Sm. These symmetry elements are not present in these stereoisomers, and therefore 2 and 3 are optically active. So the stereoisomers 2 and 3 are actually optically active. Optically active. However, this is optically inactive because of the presence of symmetry elements. This is optically inactive. Optically inactive. Now, such stereoisomers which contain more than one stereocenters and are optically inactive because of the presence of symmetry elements like plane of symmetry, we say such compounds as meso compounds. So here I have written down a small definition. Meso compounds are optically inactive member of a set of stereoisomers consisting of two or more stereocenters and contain a plane of symmetry. So you can easily define, you do not have to exactly write like this. You can say for yourself just now what I said, that stereoisomers which contain more than one chiral center and are optically inactive because of the presence of a plane of symmetry. Those stereoisomers are called as the meso compound. Those are called as the meso compounds. Okay, now an important requirement of meso compound is there should be more than one chiral, more than one stereocenter present in the molecule. Now, if I ask you what is the relationship between the stereoisomer 2 and stereoisomer 3, you can quickly say that they are mirror images of each other. They are non-superimposable. It's very important to specify this word, non-superimposable mirror images of each other, and therefore this is called as this we have already discussed this term. This is called as enantiomers. These are called as enantiomers. So what are enantiomers? These are stereoisomers which are non-superimposable mirror images of each other. So if we have stereoisomers which are non-superimposable mirror images, then these are termed as what you called as enantiomers. Now, if you ask me what is the relationship between structure number 1 and structure number 2, these two stereoisomers of the same molecule, they are not mirror images of each other, and therefore such stereoisomers of the same molecule which are not mirror images of each other, they are called as called by a term called diastereomers. So diastereomers are nothing but stereoisomers that are not mirror images of each other. Such stereoisomers are called as diastereomers. Okay. So those stereoisomers which are non-superimposable mirror images of each other, they are called as enantiomers. However, stereoisomers that are not mirror images of each other, they are called as the diastereoisomers. So I hope with this you have briefly gotten the idea of how to find out the how to get how to get the how to write the Fisher projection formula for the for compounds with more than one stereo center. Now, I'll quickly tell you how to decide the RS nomenclature in this particular video itself, because I don't want to put another video for just to discuss the RS nomenclature in a two-dimensional in a compound with two stereo center. Let me quickly tell here itself. So if I want to determine the RS nomenclature for these two stereo centers, it is pretty easy to say. So I'll consider first this particular stereo center, okay, and then assign the priority. So if I assign the priority, the first priority will go to the bromine, okay, because it's higher atomic number. Then the next priority will go to this particular carbon because it is attached to a bromine. Then the third would go to this particular carbon, and this would be the fourth priority. So now if I go from 1 to 2 to 3, it is in the clockwise direction. So it is in the clockwise direction, but since my high priority group is above the plane, and lowest priority group is above the plane, therefore it should have a configuration of S. So it is 2s. So the second carbon is having a S configuration. Okay, so let us look at the third carbon atom. So this is the carbon atom. So let me remove the these particular things here. Okay, so let me complete these lines, otherwise you'll get confused. Okay, now if I assign the priority now, first priority will go here, second priority will go to this carbon, third priority will go to this carbon, and the fourth priority is again to the hydrogen. Now if I move from 1 to 2 to 3, it is again a clockwise direction, but H is on above the plane. Therefore, the configuration of the third carbon would be again S. So we will write 2s comma 3s dibromo butane. This is how you will write in the full compound. So 2s comma 3s dibromo butane. So please write it correctly, because in my pen is not writing. There is a lag in it. Okay, so 2s 3s dibromo butane. So this is how you write the nomenclature as well. So in the same manner, please do the RS configuration for all these stereoisomers. We will discuss it again in the class. Try to discover the configuration for the rest of the uh, molecules as well. So thank you very much for your attention.